Yeah, and as you see, there are some railways here. So the slides were created by my PhD student who's a very railway enthusiast, but the whole project is in collaboration with Siemens. And if you see the steam trains, they actually put on the steam trains the most modern railway interlocking systems, ERTMS on it, because they want to run it on the main lines where there are no signals anymore. Fighting with the problems that if on a touch screens are a little bit difficult when there is a lot of smoke around. So here are the contributors. So my Harry, he did these wonderful slides for me and did, of course, all the hard work. I just am a dependent type missionary. Andy is Siemens, our industrial partner, and Monika is the boss. So, joint work with Siemens on verification of railway interlocking systems, and it's safety critical systems. So you have lots of very high safety requirements, and they are now using, after long work, they are now using the by us convincing them, they chose a Z3 prover. The important decision for them was they wanted something which has, because they deal with liability issues, so they wanted Z3 because it's supported by Microsoft Research. But the problem is SMT was they are highly optimized, and in the past sometimes they had mistakes. So you need to check the resulting proofs. And in the SAT community, before they just had such challenges, prove the theorem, and now they want the proof. And with safety critical systems, we have a much higher level of correctness. So we want to do this in a theorem prover. Now, when we tried to convince Siemens to use theorem provers, they were very skeptical because we said this replaces testing. But problem is, would you fly with a plane which is fully verified in Agda, but nobody has ever been flying with it? Yeah, better not. And I have my own example now in an area of railway interlocking systems where I developed a small toy railway, and it was fully verified. It's by Agda in this case, but trains started to disappear, and I hadn't specified that. And actually, this happened in the real world as well, that there was an interlocking system where the trains started to disappear. So testing cannot be avoided, but testing can be reduced. So the cost of testing is enormous. And then with verification, you can find errors earlier. And of course, and as well, you find the errors which say you wouldn't find during testing. So there's big progress in formal methods. So Siemens is now, 20 years ago, with the predecessors, we tried to explain to them what induction is, and now we have high-level discussions on SMT solving and the limits of Rocq and Coq and whatever. They have developed a tool chain. We have, in collaboration with them, developed a tool chain. I wasn't sure whether I can call it the Siemens tool chain or not, but it's essentially used by them now. And but they need some tools, and what they want is they need control over it. They don't want some open source free software. They need really to guarantee it. Now, these SMT proofs can be very large. My colleague Oliver Kuhlmann had this, was in the news with his the largest math proof ever, which was 200 terabyte. He compressed it down to 68 gigabyte, but still checking is a challenge. Now with proofs, with industrial tools, it's easier. So the size is not as big, but our requirement is safety criticality is much higher. Yeah. So set3 recently switched to a new format, which is based on the RUP proofs. So the old format was based on full resolution, which became extremely large. And now they use this RUP proof, which is somehow captures the essence of conflict-driven close learning. I'll explain in a moment. So the plan is the project we had is, first of all, the easy way is just to prove everything in Agda, so that was fast done. But then came the hard work to do the same thing in Rocq, which was mainly done by my PhD student. And then, there we created what he called tree proofs. Because there are lots of different kind of proof objects around. There are set3 proofs, there are unit resolution proofs, and there are proofs about the correctness, which you need to distinguish. And then we wanted to extract it into C, because Siemens wants C programs out of it. And we want it to be extensible, and we developed a 2-3 level proof pattern for carrying out these proofs. And of course, as a byproduct, we get that C proofs can be integrated into Agda. We haven't tried this out yet, how this works, but I'm confident this works. So when doing SMT solving, so we'll focus here on the underlying SAT solving part mainly. Some other PhD students are doing the SMT part of it. So we just have propositional variables. We have literals, which are positive and negative variables. We have clauses, which are lists of clauses, literals, and sequence, which are list of clauses. We split our clauses into 3 things. We have long clauses, which are more than 2 literals. We have unit clauses, which have 1 literal, and we have the empty clause. And then you see immediately a nice data type is split clauses. That's the long clauses plus unit clauses plus bool. Bool is for whether there is an empty clause or not. And then the easy thing we do what every SAT solver does is first it does the cheap things to done, which is essentially unit clause propagation. So you look at your clauses, you look for is the empty clause already there, then you are successful, you have derived falsity, because you want unsat, which means you have proved your correctness, because it's always you prove for all x by saying exist x is unsatisfiable. Now, if there's no empty clause, then you look for unit clauses. And since if you have no unit clauses, you have finished with unit clause propagation. Otherwise, you apply essentially a cut with all your clauses. So every clause which contains a negation, you remove the negation L, and you do the same with the unit clauses. And then you continue and you run this in a loop. And each time you run it in a loop, 1 literal is removed. That's important for the termination checker of Agda and Coq. And I said before, it's based on conflict-driven close learning. So what SAT solver typically does is it does unit propagation. And then if it cannot continue, then it chooses one propositional variable, and now he has to first do whether it's true and then whether it's false. So assume it chose false, and then it chooses another variable, etc., until you come to a conflict. Now, if you have conflict, you have not derived falsity, but only that this particular path was wrong. So you say now the conjunction of these literals leads to a conflict. They optimize it, so they might find out, in order to get the conflict, you can do it a bit easier. But now you have learned that the conjunction of these is not possible. And since everything is Boolean and we are classical, you have learned a clause, namely not P3 and not P7, and then you backtrack and start again. And the RUP inference essentially captures conflict-driven clause learning by simply say, unit propagation is for free, you don't annotate anything. And when you have learned a clause, you just write in your proof these learned clauses. And what is a learned clause or RUP inference of L1 to LK is if if you add the negations of L1 to LK to your set of assumptions, if you get by unit propagation or conflict, then you add it. And a RUP proof is just a sequence of these RUP steps. A RUP proof is now a sequence of, I called it here RUP inferences, and a proof of falsities, and a RUP proof which gives falsity. So, and the core of it is this RUP checker. So it takes some assumptions, some RUP clauses, you apply unit propagation to it, and then you look for success or failure. And if you failure, then your proof is fake. And if it's success, you continue. And then this is what you check in your proof. Now, so we want now to formalize the whole thing. And the purpose is really not so much understanding this algorithm, finding it is correct is not very difficult. But what we want is we want to have the guarantee. We want to have a proof that our implementation is correct. That not somewhere in this, when somebody wrote it down, you have some variable X instead of Y. So that's why we need to prove the whole thing to be correct. Now, here are the steps somehow. Of course, without having an inductive theorem prover, you could stop here and say this is hand waving, but here we go through it. So the first thing is that if you do this unit propagation algorithm, that then everything what you get there is provable from the assumptions. The second, which is trivial because you just do unit propagations when you did this cut, then you show that it's the soundness, so unit resolution is sound. So if A proves B, then A models B. And then what the RUP checker does is it takes A plus the negations of all the clauses, and it proves by a unit propagation that it's false, and if it's yes, then it says success. And by the soundness, you get that if these are it says true, then it models it's unsatisfiable, and then you shift all these negative literals to the right, and then you say, yeah, if the RUP checker proves returns true, then your all the negations were negation of your RUP formula was false. So the formula itself holds. That's the correctness. So now how to do the whole thing in Agda and Rocq. So in Agda, I used the straightforward two-level approach. We work on clauses, and then we introduce proofs of all the clauses. And it was quite interesting. Most of the work was actually on this clause level. We shift around how to define this algorithm really nicely. And once this was done, we did it on the tree proof level, and that was essentially just mirroring what you did on the clause level. Things done. However, big resistance, dependent types was really not acceptable. So I decided to, and it's really, we are talking, it was really long work to convince them to use inductive theorem provers, etc. So, so I did the soft approach and not the hard approach. The soft approach was to smuggle dependent types in. So we just have now the proof level. Instead of having the tree proof level depend on the clauses, we let them be separated. So we just have a list of proofs, a list of clauses. Now everything on the clause level works, everything on the tree proof level works, and then we add a predicate on the two, and predicates are acceptable as dependent predicates are acceptable, but dependent types are not. So I think it's a solution. Yeah, and then yeah, you just do appropriate data types and do it on these three levels, and then you get that everything is correct in Agda and in Rocq. So conclusion, so we have shown that the RUP checker, if it returns true, then this is valid, and this was proved in Agda and Rocq. We used the 2-level and 3-level approach, which I think is quite a good general methodology for all kinds of proof formats to work. And these tree proofs are not be generated. If you look at when lots of people then say, yes, in order to check it, you need to generate this resolution proof, and you check it. No, there's no need to do it, but you can do it. You can generate them, and that is additional confidence. Harry has done some large proofs of almost 5 million lines of code, which took 7.5 hours to check, which is not that impressive, but this will be optimized, I think, dramatically. You can integrate proofs from SAT into Agda. However, now, what are the limitations? Now we have the program extraction needs to be verified. And as well, that was the first question from Siemens, do you trust Rocq? So we need to somehow work in the explore how to use the trusted kernel of Rocq, which is the next step to do. Yeah. Thank you.